My name is Aleksandr Karpov. I am a PhD student from Czech University of Life Science in Prague, and my supervisor Rostislav Jakuš. Title of my presentation and my research: response of mature Norway spruce to experimental thermal and drought stress in relation to IFE SAS typographus attack, ground temperature and sapflow. What is my research objectives? First, objective: how temperature related to thermal and drought stress Norway spruce. And second, can ground temperature be a reliable indicator of water stress? And what are thermal response of spruce stands under different conditions? And how effective are spectral indices and thermal data for assessment water stress in spruce stands? Let's go to study area and plot structure. First, study area located in Czech Republic in Bohemia region. It's near the Prague. Driving on the car near 1 hour, and we use in our study 5 plots. It's trial plots, and every plot have several subplots. And I want to describe in more detail plot structure. Every plot have 4 subplots. Of course, every subplot have 10 or more trees, and every plot have 2 control subplot and 1 subplot roof. It's artificial roof that prevent rainfall, and edge that located near the forest edge and have higher solar radiation than other plots. And I want to show you how it looks like in the forest. First, it's a video for artificial roof, how it looks like that prevent precipitation and create artificial drought stress in this area. And it's how look like control sensor on the trees, and our last video includes sensor, subflow, and temperature sensors that measure ground temperature from north and south side. And about this measurement and variables that we using in our research, next is a structure of data sets that we have. Our data sets include ground data that I showed before. It's ground data include field measurement, its diameter, height of trees, and sensor measurement from sensor. In more details in the next slides, I only short described all variables here. And data sets include also remote sensing, hyperspectral and thermal data. Of course, remote sensing also include LiDAR, but it's separately now. And we use LiDAR for simulated solar radiation. It's included in one data set that we're using in our analysis. And in more detail about ground data. Here they have subflow from the sensor, measurement, field measurement, height and diameter. As I mentioned before, temperature from the north and south, temperature. Also, we have a sensor in the soil that measurement soil temperature and soil water potential. What about remote sensing data? We have 3 sensors, 2 sensors for hyperspectral, first in visual and near-infrared bands and spectrum, and second one in short-wave infrared spectrum, and third, this thermal sensor is only 1 band. And LiDAR sensor, this sensor was mounted on the plane, and survey was done by airplane. And first I want to start from LiDAR data. We have some measurement from LiDAR height of trees because I don't have all measurement for all plots from the ground, and I measure some trees using LiDAR data. I calculate standard deviation based on canopy height model that was produced based on LiDAR cloud point and canopy density indexes for density of crown and canopy density indexes with buffer 10 meters from center of each crown. And as I said before, solar radiation was modality-based LiDAR cloud punch, topographic position index, and elevation. Also, measurement using digital terrain elevation. Next slide about solar radiation, few cents about it. We modeled solar radiation based voxel approach. We use for creation with voxels. LiDAR cloud point and solar radiation was calculated for every spruce crown. And next, we use several indexes based on our spectral data. It is about vegetation index and water stress and water moisture index. In our research, I include 5 indexes. On this slide, you can see formulas and sources that I took with, and it is remote sensing data set with indexes and thermal data. It's include 5 spectral indexes and 1 temperature band. This calculation average temperature sapflow, and you can see here that control and age have practically equals value, but roof have a lower value than others. Of course, sapflow measurement in very relate with SWP, it's subsoil water potential, and you can see here that soil under roof have very low soil water potential. It includes very low average temperature of crowns. Of course, subplots from the age have higher temperature, and also roof and control practically equal and lower temperature. Next, spectral index, lowest value on the roof because roof spruce stands on the roof subplot have drought stress and a lower moisture content in the leaves, and all spectral indexes very sensitive to moisture content in the leaves, in the needles in our case. And canopy index with buffer 10 meters. Of course, it's clear that age have less density that control and roof subplot, because with subplots in forest interior and age subplot on the forest edge. And of course, it's open from the south to forest gap and have less density than other indexes for other subplots. And measurement with bark temperature from the north and south side is similar and have similar figures that temperature of crown is correlated, and soil temperature roof under the roof is lower because it's maybe shadow, because usually a roof will cover fallen needles and it can create shadow and prevent light. Next, I try analysis with data set and every variables using statistical tests. And that I take first, it was Shapiro-Wilk test and Leibniz tests. I check normal distribution of data set and every variable, and not every variable have normal distribution. And based on this, I choose Kruskala Wallis test that can work with normal distributed data and analysis significant difference for every variables between subplots. And I selected what variables have significant difference, and for next I use done post hoc test for measure do we have significant difference between subplots like a control, subplots age, or roof. And it's very similar with box plots that subflow don't have a significant difference between control A and age, but have significant difference between roof and age, roof and control subplots, and another temperature have significant difference between control and age, roof and age, but not have significant difference between roof and control. Spectral indexes practically have a similar pattern and have significant difference between control and age, roof and control subplots. Next, I plan using modeling approach for analysis every predictors, every variables, how which variables influence, for example, on subflow or temperature of chrome. And first I create parallelogram, and it shows for us that indexes, spectral indexes are very correlated with each other, and I save for next analysis for modeling only one index and exclude from this data set temperature variable with include temperature from the north side and south side and soil temperature, soil water potential, because I save only samples there we have subflow, and sometimes these variables in these samples was missed. And after we excluded, we have a data set that include 107 observation in our list and 12 variables. Half of this data set is control plots, and another half is this roof plots and age plot. First, I'm modeling temperature of Cron. Prediction variable was temperature, and we use as predictor ground data, height of trees, the standard deviation of height, diameter, soil water potential. We excluded is before, but I calculated soil water potential average for every subflow because we have a 2 or 5 sensor in every subplot, but not for each tree. And it was important variables, and I decided to save it and calculate average value of soil water potential for subflows. And we have a subflow data from every tree. Also, we have remote sensing. It is spectral index, one of them, and canopy density indexes and topographical position index and elevation is from LiDAR data, and solar data that model it based on voxel approach and LiDAR cloud point. And for this, I use several methods: linear regression and general additive regression model. And I want to show results only from GAM regression model because it's better performance than linear regression. And we slide about model selection. And for modeling, I use approach of brute force. I take from 1 to maximum 4 variables and create 100 models with a list that include all possible models with predictor from 1 to 4 in every model. And I calculate for every models information criteria for next assessment, and also was calculated delta IEs. And based on this criteria, we can select the best model and pleasurable model. Best model, it's less than delta IEs have less than 2, and pleasurable model between 2 and 7. And how you can see here that we have only one model that we can say that is our top models, because the next model already have higher than 7 delta IEs. And as a parameter, as IEs weight show for us how model fit. It's usually between 0 and 1. And on this slide, I describe a best model with include variables sapflow, canopy density index with buffer 10 meters, elevation, and soil water potential. As shown for us, p-value, every predictor is significant, and f-value, we have higher f-value for sapflow and canopy density index, and higher f-value show that this predictor have higher significance in this model. And EDF, it is effective degree of freedom. If it's near 1, it's a linear regression. It's higher. It's near the 7. It's a non-linear regression relationship between prediction and predictor. It's a more complex relationship. And this model have adjusted 71%. And next slide about partial plot show for us how this predictor influence and temperature and how it's connected. You can see sapflow that if we have less sapflow, it means that average temperature of the cone higher. If we have higher sapflow, its temperature have a less value. It's of course connected with cooling effect. If we have enough water and we have sapflow, spruce tank and cooling and temperature of course less that another the trees have a drought stress. And canopy density index with buffer 10, of course less density have a higher temperature because it's more open to sun, and so has higher solar radiation, and it have a higher temperature. Another variables, it's sophisticated, described with this manner as like less or more or increase, decrease, because it's don't have a linear relationship. It's a very complicated, complex relationship between predictor and prediction variable. Next modeling was about sapflow, and it's same slides as before, but prediction variables here already sapflow, and in predictor we add temperature, and we have same predictors that in other model, and here we have same approach and same approach for model selection. We using brute force and put in the model from 1 to for predictor, maximum for, and calculate all possible models that we have, and for every model we calculate IC and delta is, and based on this we can assessment with models, and here we have better results. We have 13 models that can be pleasurable, and 3 model here we have predictor in every model, and you can see that cell water potential on subplot practically in every pleasurable model, and diameter practical in we have less frequency for elevation and spectral indexes. I think it means that this predictor have significant role for modeling, and can suggest that diameter and temperature have higher influence on model, and based on effective degree of freedom, you can see that free predictor have linear relationship that is clear for understanding adjusted with best model, it's 48%. And we need to look on partial plot, and height is not significant for our model, and we can switch on diameter. And if we have higher diameter, we have more sapflow. I think it's understandable, because if we have higher diameter, we have more density canopy, more needles, and need more water content. It's higher sapflow, as understand in this case, and temperature. If we have higher temperature, we have less subflow measurement of the sensor. It's with free variables, free predictor have a linear relationship, and we can see how it's increased and how we connect with prediction variables, but same conditions that previous model cell water potential have not a linear relationship, and it's sophisticated to describe how it's connected in this model. And back to our objectives and what we have in the conclusion. How ground temperature relate to thermal and drought stress in Norway spruce. That we have from the statistical testing and modeling, that we have on age and control subplot practically have similar subflow, but temperature, of course, is different. Temperature of crown higher on the age subplots, but roof has similar temperatures that control data set, control subplots, but have lower subflow. It means that if we suggested only a statistical test, it is Not very understandable, I think. But if we go to model, we can see that sapflow have linear relationship with canopy temperature, and crown with canopy temperature have lower sapflow. It's and next objective is can crown temperature be a reliable indicator of water stress in the spruce stands? Yes, it's very similar with as on previous objectives that based on model suggestion, it is temperature and have significant effect on subflow. It's based on subflow we can measure stress, water stress on the spruce stands, but it's a different condition between thermal stress and water stress on the edge and the roof, and edge have higher temperature and some stands have higher temperature and have enough subflow that not, but it can be more reliable maybe for measurement stress in fluorescent air. And age, roof and age has have significant difference for a stage, and so very difficult to understand what stands have drought stands and what stands don't have, because every stand have very high temperature on the forest edge. And I think it's all. Thank for your attention.